So this is r equals 7 cosine 3 theta. And we want to show that has x-axis symmetry and 120 degree point symmetry. Now, were you able to do the 120 degree part? Yeah. That should have been okay, right? It's the x-axis symmetry that's the tricky piece on this, I think. Oh. Not really. Is that what's going on in the x-axis part? Okay. All right, so I'm just going to do like I would normally. So I'm going to replace the thetas with negative thetas. 3 times negative theta is just negative 3 theta. And then my odd-even identity for cosine says cosine of negative alpha equals cosine alpha. So I just have that, and I'm done. Is that okay there, Amanda's? Zach's? Sure. Jack, this was the same one you had? Yeah. Were you able to do the 120 part?
Yeah.
Okay. Lexi. The what part? Oh, of the limacon? Yeah. Yeah, sure. So we have 2 types, right? Y equals A plus or minus B sine theta, or Y equals A plus or minus B cosine theta, right? Those are 2 types of limacon curves. The sine ones are y-axis symmetry, and the cosine ones are x-axis symmetry. That's it. So it's that simple. And nicely, it matches up with what we know, right? Cosine's associated with the x-coordinate, sine's associated with the y-coordinate, so it's like matches up really common sensey, so it should be pretty easy to remember that. Is that okay? Sure, no problem. Anybody else on chapter 10 stuff? Okay. Today we're going to do chapter 15. Or I'm not 15. Mr. Kulik, what the heck are you talking about? I think 11. So as an aside here, chapter 11, pretty short, pretty easy. I could do this in one day if I wanted to. We're not going to do that because you have a test next period.
Please don't.
What the point of this is, what I'm trying to get at is that, like, you're going to have another test again pretty quick. Okay? It's not going to be like if we did this in one day quick, but like I can only drag my feet so much. The good news is, by and large, easy. Easy chapter. A lot of these ideas are things that are repeats from Algebra 2. So if you felt good in your Algebra 2 class, a lot of these ideas are going to be repeated, so should be okay there. In section 11.1, we're going to be talking about the complex plane. So recall from your Algebra 1 class, the complex numbers are of the form a plus bi, such that a and b are real numbers, and I is the imaginary number that's equal to square root of -1, And as an aside, that implies then that I squared is -1. Yeah, good. So those are the complex numbers, right? As an aside, little piece of vocab, we call the A part the real part, and we call the BI part the imaginary part. Everybody's okay there? So with the real numbers, one of the features of real numbers is that they're orderable. So I could ask you to do things like order these numbers from least to greatest, and I could give you like 0.83 and like 5/6 and like 10/13 and 7/9 and the square root of I don't know, like 3/5 or something. How would I do that if I wanted to order these numbers from least to greatest? What's that? Why? Well, you squared a small number, it makes it bigger. Like a decimal, something between 0 and 1. Oh, come on, guys. This isn't that hard. Put them in your calculator. Look at the decimal approximation. Sort them by the decimal, right? That's the beauty of the real numbers. Every real number has a decimal approximation, then it's easy to sort them from least to greatest by the decimal. Everybody agree? So 5/6 is a little bit bigger than 0.83, 10/13, the smallest one so far. 7/9 is a little bit bigger. And then the one that we weren't sure about, the square root of 3/5, is not the smallest, right? So what do we have? We have 10/3, and then the square root, and then we had 7/9, and then we had 0.83, and we had 5/6. Everybody's okay with that? Can we do the same thing with complex numbers? How would we do this? What do you guys think? Any ideas? Can I take this and get a decimal approximation out of it? No. What? How? Well, it's a trick question, guys. We can't do this. So inequalities aren't defined between complex numbers. So you can't say one is bigger than the other. Weird. Okay. So if there is no like least to greatest ordering for complex numbers, can we put them on a number line? Nah, man. So how are we going to represent where they go? Well, it turns out we need a two-dimensional system to order them. We instead need a complex plane. So we're just going to draw a two-dimensional axis instead of like a one-dimensional axis like we do for a number line. The horizontal axis we call the real axis. The vertical axis we call the imaginary axis. So if I wanted to say plot 4 plus 3i, I would go 4 over on the real axis and 3 up on the imaginary axis. And there's 4 plus 3i. Or if I wanted to do negative 2 plus I would go 2 to the left on the imaginary axis and 1 up. Or 2 to the left on the real axis and 1 up on the imaginary axis. Was this basically the same as plotting points, right? Same idea, not decidedly different. Everybody's cool with this? So if we think back to what we did with real numbers, when you're first learning arithmetic for real numbers, like adding and subtracting, how did you learn adding and subtracting with real numbers? Use the number line, right? Like if you had 3 plus 2, you counted 1, 2, 3, and then you counted 2 more spaces. So you knew that was equal to 5, right? Does this look familiar? Like basic, early elementary school, kind of like, this is how we add. It's basically just counting. If we apply the same idea then to things on the complex plane, if I add these two things, well, that means I'm going to go 2 spaces to the left, right? I go 4 plus 3i, and we'll go 2 spaces left from there, and 1 space up. So what's the observation there? How do I add 2 complex numbers? Just add the real parts and the imaginary parts, right? Very straightforward. Everybody agree? I just want to connect the complex plane to this so it doesn't feel like, why are we talking about the complex plane? So, so we have here for a plus bi plus or minus c plus di, we get a plus c plus or minus, oops, we should probably, that goes there. B plus or minus D I. So again, this is just fancy for just, you know what to do. Combine like terms, right? And works the same way for subtraction. Everybody agree? Not a big deal. So what if we had something, for example, So let's say we have the complex numbers z1, z2, z3 that are defined here. And I wanted to do 5 times z1 plus 2 times z2 minus 1.5 times z3. Is this really any kind of a problem here for us? No, man. We just dump in the values for these things. You know, distribute things through. Sure. Sometimes you just go going. I got excited about the math, and then I just wrote the 4 instead of a 1-4. Thank you, though. I appreciate it. If I make a silly mistake, please point those out so it doesn't get, you know, it's not like 15 minutes later. It's like, hey, Mr. Kulik, back on that example from 25 minutes ago. Shouldn't that have been like, oh my goodness, all right, let's go see. But yeah, you catch me doing something silly, please point it out. Everybody happy with what we did there? Very easy, right? No big deal. All right. Next piece. So for a real number, what does the absolute value of a real number mean? Great. So it's the distance A is from, actually let's make that a different letter so it doesn't look like a word in my sentence. K is from 0 on the number line. So for example, here's my number line. If I want the absolute value of -2, -2 is here. So 1, 2 distance from 0, right? Everybody feel okay on that? Very basic, right? Again, we've probably had that definition for, I don't know, 4, 5, 6 years. Probably saw that in early middle school laid out, right? Sounds about right. What if we want to now extend this for complex numbers, though? Do the complex numbers live on the number line? No, man, where do they live? On the complex plane. Okay, so it's still going to be a distance. Is there 0 on the complex plane? Yeah, let's call it the origin. It wouldn't be wrong to call that 0 since it's basically 0 plus 0i, which is still just 0, but we'll call it the origin because that, I think, is a little bit more intuitive as to what we mean. Okay, so let's take our complex plane. Boop. And here's some complex number a plus bi. So this is our distance. That must be the absolute value of, oh, I need to give that a name. Kind of the standard is to name complex numbers with z's. I don't know why, that just kind of is kind of standard in mathematics. That's why I'm using z's for all these complex number values. It doesn't really matter. But if you're like, why do you keep using z's here? That's why. That's kind of the standard. All right. So that's what we mean, right? Everybody's cool with that? How do I find that distance then? Yeah, so I could use the distance formula. So if I think about this is the point like A comma B, and this would be the point 0, 0. What does that really simplify down to then? Yeah. The square root of a squared plus b squared. Boy, that looks familiar, doesn't it? What's that the same of that we just recently were talking about? Magnitude of vector, and even more recent than that. Just in the last chapter. It was the R for a polar coordinate, right? The conversion between a polar and rectangular coordinate. So oftentimes we'll call this value also R. And here, when we discuss complex numbers, rather than using the term absolute value, we'll often use the word modulus. Modulus is just a fancy mathematic term for like the distance. Now, sometimes that distance is like a linear distance like the distance formula. Sometimes it's a one-dimensional distance like an absolute value. Sometimes it could be like we call it like a taxi cab distance, or if you're moving on a grid, like a street grid where you want to go from like here to here, you'd have to like travel on the streets. Like that's an interesting distance to define because, you know, transportation related problem, that's like how vehicles have to move. They can't just like drive through the middle of the blocks, right? Well, unless you have like, you know, a dirt bike or something, maybe you could do something. But if you're in a city, there's buildings in the way, and that's just not feasible. Anyways, that's just like a more generic term. That's why we have that, because not all the time is the distance like really a distance formula distance. It could be something else. Or you could have something that's just not in a space where like the triangle inequality holds, that like the shortest play from 2 points is like the straight line. Because it's really not that way on the earth. Right? Why? It's not flat, right? You're on a curved surface, so like the fastest distance between 2 points isn't always a straight line. Now, over a small, because the earth is very, very big, the curve is very, very slight. So like, you know, from like here to there is a straight line. But if you're traveling from like New York to Beijing, you know, like the path you'd want to actually take isn't the straight path. It's, you know. Anyways, this is a completely beside the point. I'm just kind of off on a tangent here. All right. Okay, everybody feel okay about the absolute value of a complex number, what we're doing? So we might also describe this angle that the complex number forms. This value we call the argument. Well, sometimes anyways. And what does that value gotta be related to? Tan theta is going to be B over A. Boy, is this looking familiar yet? Yeah, it looks like incredibly familiar. Everybody's still doing okay? So if I take these two things together, the modulus and the argument, that also describes the location of that complex number z, correct? So this creates another way to describe a complex number. We call this the trigonometric form. So basically what we have here is that our complex number A plus BI, we can replace the A with a R cosine theta and the B with an R sine theta, and that'll simplify down into our complex, our trigonometric form. Boy, does this look familiar yet? This is basically the same thing we did with polar coordinates, just like last chapter. Boy, it's nice when this happens, when it's like, hey, this is really the exact same structure, and it's working exactly the same way. Yes, we're talking about different objects, but like, whoop-de-doo-doo. It all works the same. This is one of the things that I think makes second semester a little bit easier than the first semester, is that like, you get a lot of repetitive behavior because you have so much, a lot of these things have the exact same structure, which is nice, right? Like, cool, we're doing the same thing. Lovely. Call it a different name. I'm cool with it. All right. So for example, if we want you to find the trigonometric form where theta is between 0 and 2 pi, for the complex number -2 plus 5i. So what we need is to write it in this form. So I know that r is the absolute value of z, which is going to be the square root of -2 squared plus 5 squared. That's the square root of 29. Everybody's happy there? So to find my theta, I'm going to draw my picture. So I went 2 over and 5 up. So I'm looking for this angle, theta. Well, to find that, I'm going to draw my reference angle alpha. Oops. The other side of my angle alpha is at pi radians. Notice because the problem asked us to give theta between 0 and 2 pi, I'm using pi there instead of 180. So what can I say about the value for theta? Well, it's going to be pi minus alpha, where alpha is the tan inverse of the absolute value of b over a so I'm going to do pi minus tan inverse, and then I'm not going to deal with the absolute value on my calculator. I'll just do that part in my head. Quick check to make sure I'm in radian mode before I press enter. I am, so I do. So I get 195 for theta. Is that right? Pi minus tan inverse of 5 over 2. It's not what I have written down on my sheet of paper. That's weird. Oh yeah, never mind. It is. That's fine. Good. I was looking at the wrong spot. Okay, so what do we say? We say z then is the square root of 29 times cosine of 1.95 plus I sine 1.95. And I'm done. Boy, Mr. Kulak, it seems like that's about the 8th time I've had to do that, like draw the picture and do quadrantal minus tan inverse of something, right? How many times have we done that now? A lot, right? It's at least 4 or 5, right? That's come up in a bunch of different places. Boy, that's an important skill, isn't it? What if we wanted to go the reverse direction? You know, what if we wanted to write in the standard form? Bless you. Hey, you're welcome. So when we say standard form, we just mean like that A plus BI form. Well, what am I doing here? Well, I'm just going to distribute the 4 through. And then I'm going to do cosine of 3 pi over 4, sine 3 pi over 4. Now, I could do that on my calculator, but I also observed that, hey, those are unit circle values, right? I could just read those up off the unit circle. Anybody remember off their top of their head what cosine of 3 pi over 4 is? Too slow. Negative root 2 over 2. Here's the easier one then. What's sine of 3 pi over 4? Too slow. Positive square root 2 over 2. And then we just do our multiplying. So we have negative 2 root 2 plus 2 root 2i. And maybe I'll be a little bit careful there and put the little close on my radical so you can tell the I isn't underneath the radical. How do you guys think? It's pretty easy. Not bad, right? Same kind of thing we've been doing. Nothing too tricky. I'm going to stop here. At this point, we can do up through 40 and the homework set. Now you're like, goodness gracious, 40 problems. Look at how hard these problems were, though. Like that's like you just doing like the distance formula and stuff, and like doing things that we've done a million times. None of these are super duper time consuming. So I know 40 is a lot. This is part of the reason why we're only doing one section today, and not doing the whole thing in one day. Even though we could, it's not so difficult that we couldn't burn through the whole thing in one class period. But we're going to stop here. So I would say, what do we got?